Korlakai Vinayak. So Ramya is at the University of Wisconsin-Madison. She was named the Rising Star in Data Science Workshop, and she received the Schlumberger. I say it in French. Yeah. Yeah, so it's a pleasure to welcome you as the first speaker of this workshop.
Hi, everyone. Thank you again to the organizers for organizing the workshop and inviting me. And thank you, everyone, for making to the first talk of the workshop. It's really a pleasure to be back here in Seattle. I was a postdoc working in this building before I moved to Madison. Today, I'll be talking about learning from diverse human preferences. I will start with some motivation. I'll talk about personalizable reward modeling for alignment, a few results on sample complexity for learning these personalizable reward models, and I'll comment a little bit about some limitations of learning with limited preference comparisons and end with some real data experiments. And most of the talk will focus on the first three papers that are listed here. I'll not have much time to talk about the last one, but there we were looking at, instead of learning preferences, learning like distribution of preferences. And if you have like extremely few samples per person, say one preference comparison per person, like what are some of the issues that arise in terms of identifiability and so on. So I'm happy to talk about that offline. But let's get started with the motivation. So the lot of these frontier models or foundation models which get trained on enormous amount of internet scale data, like large language models or diffusion models for image generation, they don't get deployed immediately. Right? They undergo a lot of fine tuning before they are released to the public. And one of the stages of fine-tuning involves what's called preference alignment. So this is usually done by taking lots and lots of preference comparisons. Like you have the generative model where there's a prompt that goes in. You have a couple of generations that come out of the model. Humans are asked, like, do you prefer A or B? And you get a lot of these preference comparisons, and using them, you try to make the model move towards producing outputs that are more preferred by humans, right? And it's done in very many different ways, but I'm going to describe a very commonly used method, which either you explicitly or implicitly learn a reward function that's supposed to mimic human preferences, and then you can either use them to fine-tune the model itself, or you can also use it during inference time, where you keep the model as is, but you adjust the outputs using the reward function to output the more preferred response. So the goal of this reward function is it takes in both the input prompt to the model and the output generated by the model as the input and spits out a number. And the higher the number, the more preferred the output would be by human. Okay? So in today's talk, I'll be focusing on learning these reward functions. And as I mentioned, it could be used in different ways downstream, either to directly fine-tune the model, or more practical when you're trying to do personalization would be inference time methods, where you don't try to fine-tune the whole model, but adjust the outputs during inference time. Now, so I mentioned learning from diverse human preferences. We want to have alignment, but for plurality. Now, what do I mean by plurality? Right? So when we think of aligning these AI models to human preferences, it's a natural question that arises as to whose preferences, whose values are we aligning them to. And last year, with folks from UW here, there was this ICML paper that came out kind of identifying this issue that most of the approaches that existed for AI alignment through RLHF was focusing mainly on just aligning, assuming that everybody has a single preference or single value, but that's not really the case in reality. In this room, perhaps we all have different preferences and values, and therefore it's important to kind of start with the assumption that we have different diverse values and preferences, and how do we now learn them? How much data do you need per person when we are collecting this preference data to be able to learn heterogeneous reward models? And while I'm motivating this talk through learning reward functions for AI alignment, things that I will present is also applicable to recommendation systems, right? So mathematically, like what we will be looking at has a wide range of applications apart from AI alignment in recommendation systems, in behavioral and cognitive psychology, and social sciences, opinion survey research, and so on. So if we look into the papers that focus on RLHF for AI alignment, whether it was the 2017 OpenAI paper or following that, there is several papers that look at AI alignment to human preferences. But if you look at the modeling that goes into it, most of them essentially are using the Bradley-Terry model, right? So if we look at what Bradley-Terry model is doing, it's looking at the probability of one alternate being preferred over the other given some prompt. So here I'm denoting XC to the context or the prompt that goes into the model. XL and XR are two generated outputs. So the probability of XL being preferred over XR for this input prompt is given as the sigmoid of the difference of the scores for these two prompts, right? So if we dig a little bit deeper into Bradley-Terry model, the assumption that goes into it is that if you take all the alternates that are being compared, let's say they have some true weights or scores associated with them. If I knew these true weights, I could just arrange all of them according to those weights, and that would give me the preferred ranking across these alternates. Now, when we query for a pairwise comparison, we might get some noisy observation, and that noise is modeled as this ratio of the winning item's weight divided by the sum of the weights of the two items being compared, right? So there is an assumption that there is a single ordering that you could do if I knew the true weights, and the goal is to learn the weights, right? So that our function is trying to learn a function that maps to get close to the true weights. So by using BTL model for learning, we are inherently assuming that there is a single preference or single ordering of things being compared. And also, the other aspect is that there is a assumption of like the function for noise as well. So the noise is modeled as a sigmoid function here. Around the same time as Bradley-Terry model came out, there's also another model called ideal point model, which was proposed by Coombs in the psychology literature. And Coombs' model is also trying to model human preferences. It also falls into the broad family of linear stochastic transitivity models. But Coombs brings in some geometry into picture. Let's assume that the alternates that are being compared have some representation that we know in some semantically meaningful representation space, which means that if two items that are closer in their features are actually kind of similar to each other, items that are far away are different from each other. And the idea of Coombs was to think of a user or a user's preference as a latent vector in the same space as these items. And how much this individual prefers different items is inversely proportional to how far away the items are from the user's preference point, right? So now if you ask this user, do you prefer tomato or pear? The answer is going to be a function of how close the tomato is to the user's preference point as opposed to the representation of the pear. And you can also put a probabilistic model on top of it to capture noise. And here the function h is a link function. It is strictly monotonic with when the distance between the alternates and the user preference point is 0, then it's fully noisy. But if that's not the case, then the farther away the differences of distances are, the less noisy the answer is. Okay? And sigmoid can be one such link function, but you can have any link function that satisfies this assumption for the link function, and that would be fine. Right? So here, so essentially if you use sigmoid, it would be Bradley-Terry model, but with a very specific function for rewards, which being this distances of the objects from the user preferences. So any question at this point about either Bradley-Terry model or the ideal point model? Okay. And there's rich literature on ranking by pairwise comparison, both in the Bradley-Terry model and in the ideal point model. Like Kevin had, I guess, his works, and Kevin and Rob had like this active ranking paper with preference comparisons. So there's been a lot of work understanding like how many samples would you need to learn ranking using these kind of pairwise comparisons. There have also been works that look at localizing the user preferences in the ideal point model by making pairwise comparisons. But these are like, again, like universal models. They're assuming single preference ordering. And also in the ideal point model, which we will be working with moving forward, most of the algorithms assume that you know the distance function. So the metric under which you are measuring how far away things are in the space that you're working with. So in practice, however, people have different preferences. And also in applications that I was motivating with, if you think about where the representations of these items or outputs of generative models and so on are coming from, maybe we can take penultimate layer representation from the neural networks as the representations, but assuming that Euclidean distance in that space or angle in that space is the right way to capture human beings' notions of thinking about similar and dissimilar might be too strong an assumption. Right? So we want to kind of move over that. Now, when we think of building in the heterogeneity, in the ideal point model, it's quite straightforward to bring in the heterogeneity. If we have n users, each of them having different preference points, then we assume that each person has their own unknown ideal preference points. And so when you query a person, let's say user K, with whether they prefer tomato over pear, now their answer actually depends on how far away the two alternates are to their specific preference point. So now if I ask the same question to Rob, and if I ask the same question to Miriam, or if I ask the same question to Siva, they might give different answers, not because it's just noisy answer of the same comparison, but noisy, it's not, it could be like different because each of them have actually different preferences over those items, right?
Is the game ultimately to embed all of the items and all of the users in the space?
Yeah, so you start with the items embedded in a space.
So you start with that.
They start with that. Users, and I will talk about like modifying that a little bit very soon. And user preferences are unknown. Yeah. So we don't want to assume that knowing the distance function. So what we're going to do is actually also learn a distance function, or rather you can think of a mapping on top of the original space that you're starting with, so that in the mapped space, we are going to use Euclidean distances to be the distance measuring the items and the user preference point. Okay? And so our goal is going to be learn both that unknown mapping, and I'm going to assume that unknown mapping is shared across people. So our notion of whether an apple is closer to a tomato or broccoli, that notion is shared across everyone, but we might have different preferences as to whether we prefer apple or we prefer pear more, and so on. And I'm going to present some results in terms of sample complexity for learning this problem. And for that, I'm going to particularly look at mappings that are linear. So you can think of them as like, having just a fully connected linear layer on top of whatever neural networks, penultimate layers representation you're taking. But you can, equivalently look at it as learning a Mahabalonis metric on the space that you were working in. So to recap, we are trying to learn the preference points of n different users, and a common unknown metric from pairwise comparisons. And what we're going to do is to essentially throw the usual approach at this, which is trying to minimize the empirical risk. So note that for every person, you have a bunch of pairwise comparisons that are collected, right? So item I, item J, which of these two do you prefer to user K? They give some answer. And so you collect lots and lots of that data. And then, so Y here denotes the answer given by the user for user K for the pair that includes I and J. And some, we're trying to minimize this loss function. Think, this loss function could be, our result covers a variety of loss functions. You can think of, for example, a logistic regression or hinge loss. And the constraints here essentially are constraints that are trying to say that the user preference point shouldn't be too large. The metric cannot be unbounded, and so on. And if you have more structure on your metric, you could also enforce that. For example, if you're looking for a low-rank metric, you could impose a constraint that's trying to encourage that. And also, if you expand this form here, what we notice is that the user preference point U always ends up like showing up along with the metric. So you can also reformulate the problem instead of like trying to learn U's to just learn these modified user preferences V's. And in the constraint here, as I've mentioned before, you can either just bound the metrics like a norm of the metric, or if you want to encourage low rankness, you can include, for example, a bound on the nuclear norm. And here I'm involving both the M and the V1 through Vks because V1 through Vks are coming from this mapping that includes M. For more details of the optimization itself, I'm happy to talk offline. Miriam, you had a question? Yeah.
Yeah, so if you fix the M, is this just clustering problem, or is it different?
So in this one, it's not the clustering aspect isn't come up yet. I will come to that in a few slides. If you fix M, it will go back to learning the user, just use. So it's like, so you're assuming that identity, let's say you put M equal to identity, for example, then you are, in the original space, you're assuming Euclidean distance is the distance function that represents people's way of thinking about similarity and dissimilarity. And I'm going to then focus only on learning the user preference points. Yeah. Then it's just localization problem. Yeah.
So in that case, you're talking about what you're doing, you're fixing the items in the space, and you're just choosing whether UKs to be consistent with the group.
Yeah. So right now, in this setup, we don't know the M either, so we have to learn both that and the user preferences. So if we use this kind of approach, what we can say is if you look at the excess risk with the learned metric and the learned user preferences and compare it to the risk with the optimal M and the optimal V's, then the excess risk is bounded by a term that's in the numerator. So S is the total number of pairs that's in the denominator. In the numerator, we see a d squared plus nd. To recall, we are in the representation space is d-dimensional, and n is the total number of users, right? So here we have not assumed any structure across users or anything like that. So each person could have their arbitrarily different user preference points. So if we think about it like the metric, if it's full rank, then there's order d squared degrees of freedom to learn the metric. You have n users, each person has their own preference points in d-dimensional space. So roughly d squared plus nd is the total number of degrees of freedom that we are trying to learn. So if you had only one user, then you'd have to put the burden of learning both the metric and their preference point together. So you'll have to ask d squared queries. But if you have at least d users, you can get away by asking only order d queries per person and amortize the cost of the learning the metric across the users, right? So this is kind of nice because even if I knew the metric, if the metric were full rank, I would need to ask order d questions to learn the user preference point itself. So, so after this, we were kind of wondering, so this kind of allows us to kind of answer both is it possible to learn the metric and the user preference point simultaneously? Yes, and also it's nice that we can do that by asking roughly just order d questions per person. But now, do I have to ask order d questions, right? So if you take like representations, for example, let's say I'm trying to do reward learning for a diffusion model, and I take representation coming from CLIP. So you have something like, maybe of the order like around 1,000 dimension that you start working with. Now, am I going to ask like, Kevin and Rob and Siva and Miriam, everybody 1,000 questions? That's not going to be like a fun thing to do for the user to provide that many responses, right? So if you think about, can we learn with less than order D queries per person? So we asked this question in terms of like, what if I even didn't worry about learning user preferences? What if I wanted to just learn the shared metric? Is it possible to do that if I didn't care about localizing the user preferences? And it turns out, in general, no. So we have a general impossibility result. So in terms of like, we have a technical definition of what generic pairwise relations are, but at a high level, like what it means is that if there is no structure in the representations of the items, and if there is no structure across user preference points, then essentially there is no structure to really exploit. Then you have to ask order D queries per person in order to be able to learn even just the metric. And in this paper, we also kind of looked at what could be different structures. In particular, in last year's UAI paper, where we were focusing on this limitation of learning the metric with small number of preference comparisons. After like this impossibility result, this means that okay, if there is structure, maybe we can exploit it. And first, we considered structure in the items. Let's say that when you're comparing different things, there is some semantically meaningful subspaces where subgroups of items can fall in. And if that's the case, like what can we do? So a natural algorithm in that case is that you query order the dimension of those subspaces, number of queries to users, and try to learn the metric restricted to only that subspace from those queries. And then as long as the subspaces all together span the whole space, you will be able to stitch back the metric together. And we have results on like what is the quality of that and so on. But in the interest of time to kind of move to structure in the user preferences, I'm going to take the rest of the time to think about what about structure in user preferences, right? So to go back at the modeling that we are working with, we have this pairwise comparison model where each user has their own preference points. And learning, like if I really wanted to also learn the user preference points, then if I don't assume any structure in the user preference point, I would have to make order the number of dimensions in which I'm learning the user preference points. So a natural question then there is even though we all have different preferences, there could be some commonalities that exist across us. Can we exploit that? And that's what we do in leveraging that to be more sample efficient per person to learn personalizable reward functions. To go back to the modeling problem, what we do is bring in mixture modeling along with the ideal points. So Miriam, this is where like the clustering like idea comes in, is to say that, okay, I have this reward function that is this distance between the item and or like the output of the generative model concatenated with the prompt and a user preference point. But maybe these user preference points are not just arbitrary, that each user preference point can be written as a convex combination of some prototypical preference points, right? So now let's say we are all the people in this room are all users, and if I look at each person's user preference point and stack them into a matrix, this assumption means that this matrix can be written as like A equal to P times W, where P is going to only have P is the prototypes, and the number of columns in P is K, where K is the number of prototypes, right? And W is capturing the weights. So now the mapping F and the prototypes P's, P1 through Pk, these are shared across the population. The weights are different for different individual. Yeah.
How are the UI used to denote the...
Oh yeah, so the UI is A here, yeah. So, so now the goal is from pairwise comparisons across the population, I want to learn the mapping, shared mapping F, the shared prototypes P1 through Pk, and for each individual I also want to learn their own weights so that I can get the personalized preferences predictions for them. And there are two types of generalization we care about. The generalization result that I presented before, those type of generalization results I'm going to call C inaccuracy, because there we are talking about how new preferences are made for the people in the data set. So these are the people that you have seen in the data set, and you're trying to understand how you could predict new preferences for these people. But we also want to be able to do unseen user preference learning. That is that if a new user comes in, I want to be able to quickly try to localize them and predict their preferences. And for a new user, what we're going to do is to keep the F and the prototypes P fixed from what we have learned using the data set, and only learn the weight vector W. And then we'll be able to predict for them. To recap, we are trying to learn the unknown metric or mapping F, the prototypes, and the user preference, the weights, using pairwise comparison data. And again, we are going to use empirical risk minimization approach by now throwing in extra structure onto the problem. So to highlight here, we're going to have like the weight vector W, and then the instead of like the user preference point being arbitrary, we are going to say that, oh, we must be able to write them as like taking some k points and then being able to kind of put them with their respective weights. And the results for sample complexity are going to be in the setup where the function f again is a linear function. But when I provide you the experimental results, we also did experiments with learning small neural networks, which works well in practice for a lot of interesting applications. Now if we look at what is the sample complexity for seen users, so this is looking at how well will we predict new preferences for the people in the data set that we learned preferences for. S, to recall, is again the total number of pairwise comparisons collected. So the numerator here now has a d square plus kd plus kn. To recall, d is the dimension we were working with, k is the number of prototypes, and n is the number of users, right? So the order of degrees of freedom for the metric is still d square. You have k prototypes in d dimensions, so k times d. And then for each user, the individualized metrics, the individualized preference points can be now written using the weight vector. That's the individualizing factor. And for each user, you have a k-dimensional weight vector that you're learning, right? So that kind of checks out. So what does that mean now is that if you have large number of users, now you don't need order d queries per person anymore. Because we are trying to exploit this shared structure across user preferences, you now need only order k queries per person. And usually, if the number of prototypes is much smaller than d, you can get away with much fewer queries per person and still be able to do preference prediction, right? And if we think about unseen user, when a new user comes in, we're going to keep the m hat, the metric learned, and the v hat here is like m times the prototypes. So, so the v hat or the prototypes learned fixed. And I'm going to only learn the weight vector for this new user, right? So now if I try to look at how well, like if I have a new user who is randomly drawn from the same population as the data set that I had collected to learn my metric and the prototypes, then and if I look at the excess risk with the W that is learned for the user, but along with the m hat and the v hat that was learned from the data set, compared to actually the optimal m star, v star, and the w star, then the excess risk is bounded as follows. There are two terms here. The first term is actually to do with how well is the m hat and v hat to begin with, right? So if we haven't learned the metric and the prototypes really well to predict well for the seen users in the first place, then there is no hope in trying to do well for like unseen user magically, right? So the first term is just looking at have we done learning the metric and the prototypes well. So the second term is what is kind of capturing the, so the first term, you should think of it as being very small if we have done good job with the seen users in the first place. And the second term is k over m is telling us that like m is the number of samples I'm taking from this new user, and roughly that needs to be of order k, right? So essentially with the same order of comparisons as we had demanded from each user to learn in the seen user, like learning the m and the prototypes, with order k queries, you're also able to predict well for the new user. So if we look at the setup and try to kind of simulate this and see how do we kind of try to figure out how many prototypes to use and so on. So if we'll try to focus on the second, the second plot here. So here we are looking at the test accuracy versus if you had different number of true prototypes, and for each of them we are looking at different number of prototypes put in the model, right? So what we see here is that as you increase the number of prototypes from 1 to 2 and so on, after the actual number of prototypes, there isn't really much of an improvement. So that's a good sign in the sense of it tells us that we can use cross-validation to actually pick the number of prototypes needed to capture the heterogeneity in the data set. And taking these ideas of like, okay, we have this sense of like how many samples would we need per person to be able to like learn both the shared metric and user preference point. Now we want to take these ideas and see how well these ideas can translate into some of the real world problems we started with the motivation, right? So in many of these applications where you have some prompt and like two outputs, instead of thinking about ideal point as this like fixed vector in some space, it is more amenable to actually think of like an ideal mapping of the input prompt. And what do I mean by that? So think of like a diffusion model. Let's say I want an image of a cat. That's the prompt that's going in. And a cat image is generated, or some image is generated by the generative model. So there is two different outputs. Let's say two images that are generated. Let's take some representation. Let's say clip representation for those images. Now this prompt, if the prompt is being input by me, let's say that gets mapped to that point shown by the green arrow. But if instead, Daniel wanted an image of a cat, that prompt gets mapped into a different point in the shared space, right? So now for the same prompt and the same outputs, which of these two outputs I prefer is going to be different than which of the two outputs that Daniel prefers. So essentially, what we are looking at in this case is you have this reward function, C is the prompt and X is the output. You are now mapping the prompt and the output to the same space, and the mapping of the prompt is personalized. And now this mapping is again assumed to be a convex combination of k prototypical mapping. So this is a similar idea of shared structure of mixture modeling that is coming in. So for this prompt, if I now look at where it gets mapped to for each of the people in this room, if I look at that as a matrix, it still is kind of factorizing into a low rank matrix. So the G here maps is the prototypical mappings, and W's are the weights that personalizes these mappings. Again, it's the same kind of question of both seen and unseen user accuracy that we are interested in. And also, when it is an unseen user, we keep the mapping F and the prototypical mappings G's fixed, and only learn the new weight for the new user to predict. First, I will show you some experiments on text-to-image generation settings. So this is a data set called Pick-a-Pick. And this data set has been collected where like humans go and like input some prompt, the model outputs 2 images, and then they say which image they prefer. And when we were running these experiments, the state of the art was pick score. And we were able to actually get similar performance as pick score, but using way fewer number of parameters, right? So pick score is essentially fine-tunes 20 layers of clip, last 20 layers of clip. Whereas what we did is just take the clip embeddings and learn just 2-layer MLPs for F and the prototype functions, and able to get essentially the same performance. Interestingly, Pick-a-Pick also has like a version 2, and we also looked at what happens if we take the training from training data in the version 1 and look at how well it translates to the test set of version 2. Pick score actually drops a few percentage points in its performance, whereas we are able to actually keep very similar performance. And our hypothesis as to why this is happening is because we don't really mess up with the clip embeddings, right? So I think this is the other thing of like when we try to fine-tune foundation models a lot for the specific data set to get good numbers on that benchmark, we might lose the generalization into slightly, even Pick-a-Pick V2 is not a different data set, right? It's collected exactly using the same method as V1 was, but of course there's always going to be some shift when you collect the same type of data set. And even with that, pick score drops performance, whereas PAL is able to keep the performance, and again, like the similar performance as if you were to train on Pick-a-Pick V2 and test on the test set. Now I'll talk a little bit about some experiments we did with applications with just text-to-text, so language model setting. So this is a data set where you have some Reddit summaries, like Reddit posts that have been summarized. And this is more of a semi-real data set. So you have this data set's created with like having 2 subgroups of people, one group like preferring smaller summaries or shorter summaries versus the other preferring larger summaries. And when we did this experiment, the state of the art was essentially looking at like training a really large language model, and we were able to get similar performance again, but with much fewer parameters. And I want to highlight here that this approach of modeling that I described gives us a lot of modularity, right? So you can pick which model, foundation model you use to get the initial representation to begin with. You can pick what is the function class that you're going to use to learn the F and the prototypical functions G. And in fact, it turns out that it might be beneficial sometimes to actually use different foundation model than the one that even generated the data set to do the initial embeddings. So my students did like a lot of hard work in trying to look at what the test accuracy would look like as a function of like different number of parameters being used. And if you look at the test accuracy on the y-axis and the number of like learnable parameters, so the orange point there is the previous state of the art. This point here is what I have shown here, where we used OPT 350, and we also actually fine-tuned that a little bit. And then if you use larger and larger language models, you can actually get better and better performance. But then we were interested in like the other side. What if we have limited resources and we are using smaller language models? Turns out that if you use DistilBERT with just 65 million parameters, it actually performs on par with these like much larger models that we had worked with. And if you push it a bit further and then keep the DistilBERT parameter fixed, not touch it at all, and learn only 2-layer MLPs on top of it, you can get nearly like 90% performance, right? So what I want to highlight here is that with good encoder models and being careful about like our model selection, we can actually get pretty good reward functions with fewer parameters than actually throwing at all the resources at learning these. In terms of like the results for unseen users, we also like look at what happens if we are like trying to predict for new users, just learning the weights, and using like different number of comparisons to learn the weights and see how well you do. Even with like around 10 comparisons for the new users, you can get roughly close to the performance as for like a user in the data set, right? So that kind of checks also from like our like understanding that theoretical results that we saw before, that roughly using the same, like in the data set also there is around tens of queries per person when we were learning prediction for the seen users in the data set, and similar number of queries per person you can actually start doing well for a new user as well. And in the paper we also kind of created like small personas using anthropic personas, and tried to kind of look at how if you had more and more number of subgroups, what it looks like. So I'll skip the details in interest of time, but to highlight the advantages of like going back to kind of thinking about more about this modeling approach as we did, we can obtain a sample efficient algorithm, in the sense that now you need only order k comparisons per user to do the preference or the reward learning. It allows a modular design. So essentially we are trying to incorporate commonalities across the users to reduce the samples. But also it's an approach that's very versatile. You can take this modeling approach, apply it to image generation models, you can throw it at language generation models, you can also throw it at the traditional recommendation system setups and so on. And with that, I want to just talk a little bit about some open directions before ending the talk. The approach we took essentially can be thought of as like, especially PAL-B, you can write it as like a convex combination of k prototypical reward functions. And now you can think of, instead of where the prototypical reward functions were this of very specific form, but instead of like having that very specific form, you could try to learn maybe a slightly general functions for reward functions. And there have been like interesting sets of work that have followed up, including like Miriam's group had a very interesting paper, LORE, that looks at again low rank function classes to learn to capture these reward functions. I also want to highlight the need for better data sets and benchmarks in this setup, because when we were looking at data sets, many of the data sets didn't even have anonymized IDs, so it's you can't even like think about like learning these heterogeneous functions at that point. Some data sets that did have anonymous IDs, they were very imbalanced in like few people giving thousands of data points and most people just giving very little. In those scenarios, we will not only be able to learn the preferences of those few people that gave lots of data and not really be able to learn the preferences across all the users. And there have been some new data sets that are being constructed, which is, I think last NeurIPS, in 2024 NeurIPS, the data sets and benchmark had a new data set for alignment, which is a new step in kind of creating data sets and benchmarks, but many of them are still quite constrained in the number of people and the number of preferences that are queried per people. So it will be interesting to kind of also explore what other data sources exist, and one exciting directions would be looking at the public opinion survey and research kind of data sets that people have collected over a long periods of times, and see how we could potentially leverage some of those data sets in the setup. And this ICML, there was a really nice keynote by Frauke Couture on this. I would highly encourage you to take a look at it if this is an area that interests you. And the other is, the algorithms that I presented today, of course, were more in the passive setting for learning the prototypes and the mapping F, and the adaptation was for new users to just learn the weights. But you can also think about kind of having an algorithm that adaptively also learns prototypes, right? So what if now as we kind of start trying to predict to new users, we start discovering that we are not doing so well for a subgroup of people, and maybe we need to update our prototypes to add more heterogeneity. And also, like all the other questions that we ask in terms of generalization with respect to any ML procedure also applies here, right? So we need to also think about generalization in terms of like OOD generalization for users, OOD generalization also for prompts. Like if we train our models with prompts that only are like from a specific domain, it's not going to generalize to some other domain, right? So because we are learning then reward function really good at this place, but not like some in other domains. And of course, like in the end, if you think of the bigger systems that involves, including these kind of personalized preferences, you also have to still operate within the global safety constraints for the system. So individual preferences should not be able to bypass those safety constraints that exist for the system. With that, thank you everyone for your attention, and I'll be happy to take any questions now or also offline during lunch and breaks later. Yeah.
So at the end you mentioned that a lot of these data sets don't have user IDs or whatever. Can't you treat it as some latent variable and fit like a mixture model type thing?
That's a good question. The difficulty there, at least we encountered, is it's hard to really know what we've done and like if it's working. But that would be an interesting direction to also explore. Yeah, thank you. Yeah, so far we have very limited kind of outputs there. Things that we tried didn't really work very well. Yeah.
I noticed in some of your experiments it looked like K was equal to 2, and that seemed to give you a big improvement over no mixture,
yeah.
equal 1, I guess. And I'm just wondering, what's the interpretation? Where are these 2 prototypes in those situations? And if there are 2 bipolar-like prototypes, do we really need to consider all linear combinations of them? Or why that whole subspace or something? So
I see. So if I understand your question, are you wondering whether you could just do clustering where you could just have the 2 people?
That would be
yeah.
another one. Then it would be log K instead of K, right?
Yeah.
In terms of how many questions you'd have to ask an individual. And so I was curious, especially because it seemed like in whatever that one data set, pick or whatever, it was 2. I'm wondering, what are those 2 prototypes? And are people kind of really concentrated around one or the other? Or are there people who are really all convex combinations or linear combinations of these 2 prototypes?
Yeah, that's a really good question. For the K equal to 2 was the language model one, the summary data set, where actually it was more like a clustered setup because it was like people who like shorter summaries versus longer. So in the modeling that we were looking at, it was general to consider any mixtures. But of course, like clustering with like 1, 0, 0, 0, 1, 0 kind of weights, you can have separate ones. But the one that you were kind of alluding to in terms of like reducing the sample complexity, if you are doing it actively, like adapting on the fly perhaps, that can definitely reduce the number of queries. But I guess it really depends on whether your setup, as you mentioned, is more in the clustered setup, or is it more, it actually requires mixtures. One way to potentially kind of identify that is, I guess, while doing the initial part of like learning from the data set, the first thing that we are learning, the mapping F and the prototypes. Once we learn that, we could look at like where the distribution of the weights are. And if that looks more clustered, then perhaps for the new unseen users, you could potentially exploit that cluster structure and even reduce the number of queries. That's an interesting idea. Thank you.